Okay, so we've had our introduction to Thermo, and we're going to look at calculations. So, uh, as you may have read in the book and worked through perhaps the POGL, we'll see we end up with this equation. This is our main equation. We've got Q, which is our heat, right, slash energy. So the units of this guy are going to be, this is our joule or calorie, right? So when we see those in a problem, we know that's the Q. Our M is mass that we've been working all along, right? That's our grams. Our specific heat is that property we talked about. So each specific substance has its own unique specific heat in a unit such as joules per gram degrees Celsius. This triangle is something that means change in. Okay? It always goes along with something. It doesn't stand by itself. It's always with what comes after it. So this is actually the Greek letter delta. So delta T means change in temperature. Or if we look down here, it means T final minus T initial. Right? And as we talked about before, right, the units of this can be either degrees C or K because we're doing a change in temperature. And since these are the same scale, we don't have to convert to Kelvin or we don't have to convert to Celsius. We can actually just flip between them. There's no conversions needed when we're doing a delta T. Okay. So that is our foundation and where we are going to do all of our work in this unit. Well, almost all of our work in this unit. Okay, so I'm going to look at a couple quick sample problems. Our first problem is up here on the screen. We want to know how many joules does it take to heat 500 grams of water from 25 to 100 degrees Celsius. So when it says how many joules, right, we know that means we're solving for Q. So we're going to need to know the mass, the specific heat, and the delta T, or the initial and final temperatures. Well, we have all that, and it really just makes it a problem of plug and chug. So Q, our mass, we've got 500 grams. Our C is for water, right? So we had looked at that before, and this is a value that will be given to you. If we were in class, it's back on the back of our periodic table. It's just our specific heat of water. And then we have our T final minus T initial. That's what this triangle T is. It's delta T, T final, which is 100 minus 25 to get us there. And all we do is solve those. So mathematically, that comes out to 156,900 joules. Okay. So our joules get to be big pretty quickly. Also, we have to take into account our significant figures, which actually, in this case, is really going to be 2 because we get a 75 here when we add those together, which should get us to 160 kilojoules. Okay, so to get to my 2, I rounded here. There's a 6 next. To get from joules to kilojoules, we just put the decimal there. That gets us to 160 kilojoules. Okay, the next problem we're going to look at is, well, same application, just we're going to solve for a different variable. All right. So this time we've got joules here, so we know once again the joules is going to be Q, but we have the value, so we won't be solving for that. What we are solving for is the specific heat. So we know we want to solve for C. So if I take Q equals MC delta T, right, I divide both sides by M delta T, M delta T. So M and delta T cancel out here. I rearrange this, I find that C equals Q over M delta T. So I've got my Q value of 45 joules. I've got my mass of 25 grams. And I've got my T final, which is 25 minus 15. Okay. And we end up with a value of 0.18. Okay. Note, none of these units cancel. So we're left with units we would expect for specific heat. Joules per gram degrees Celsius. And that's the basic application of the Q equals MCAT equation. Okay, so one thing we want to note is the sign of Q, right? It tells us whether a system is exothermic or endothermic. Okay, and we say up here by convention, and that simply means that a bunch of people agreed on it. There are actually other professions that use a different sign convention, not for us to worry about. This is our convention. If it's exothermic, right, which means energy from the system to the surroundings, we make it negative. If it's endothermic, we make it positive. You should always include the sign. Okay? While we know 12 is a positive value, and we'll assume it to be when you write it, in Thermo it's always best to expressly write that positive. And of course you must expressly write the negative. And of course you're going to need a unit like joules. But that's that. So actually if you use delta T correctly, meaning delta T equals T final minus T initial, the sign will work itself out. Okay? If you make a mistake there, you can also just analyze the system, what's happening from your description, and figure out if energy is going into or out of the system. Right? This works because if it's hotter, if it's going from 25 to 100, well, hundreds are final. Right? Make that an arrow. So 100 is our final, minus 25, that gives us plus 75 degrees. Everything else in Q equals MCAT is positive, so our value will come out positive because we have to add energy to get it hotter. If we were cooling it down, it would be going from 25 to 100. That would give us negative 75, which would also make the sign of Q negative. It's getting cooler. Energy has to be flowing from the 100, which was our starting temperature, to the surroundings or whatever is the cool 25 degrees Celsius. Okay. The next term is enthalpy, and it gets this interesting letter H. It's defined as the total energy of the system, and a bit more complicated definition that we don't really need to get into. Okay. While it has some differences, for us at constant pressure, Q that we've already talked about is just our heat flow, is going to equal this delta H. So delta H will have units of like joules or kilojoules. Okay, and for us, we'll always be doing problems at constant pressure. So Q and delta H will be interchangeable. So if we think about delta H and Q in constant pressure, it really simply means that we're doing it open to the atmosphere, which is essentially constant pressure. So the next section is calorimetry, which is just, well, it's a precise measurement of heat flow into or out of a system. And really, any Q equals MCAT equation that we do is considered calorimetry, but I like to look at it when we have this process of two things interacting. Okay, so we usually use something called a calorimeter, which isn't really that fancy, and you're going to see it's even less fancy than you may think. It's just a container used, and we use this setup to measure the absorption release of heat in a chemical or physical process, and that is called a calorimeter. Okay. And so what you can see here is actually, before we go through that top part, one of our calorimeters, and the common one we would use in class, is just a coffee cup calorimeter. It's just styrofoam cups, insulated cups, an insulated lid, you have a thermometer, and something to stir it with. That's it. So this thing on the right here is a bomb calorimeter. It's a bit more complicated in setup, but at the end of the day, the thought behind them or the foundation behind them is going to be the same. So we're usually going to identify and think of this coffee cup calorimeter. While we may talk about the bomb calorimeter in terms of doing some calculations, those calculations will all be the same. So the main purpose of the calorimeter, okay, is going to minimize heat loss to the surroundings, okay, or absorbed if the thing inside the coffee cup is colder. So if you had, say, coffee in a coffee cup, you're usually trying to keep energy from leaving the coffee, making the coffee cooler. If you have like ice water, you're trying to prevent energy coming in. You want to keep your ice water cold. Okay. And while the coffee cup and the stirrer and the thermometer can absorb some energy, well, they do absorb some energy, it's usually minimal, and at this level we just most often ignore it. So there's a big idea here in calorimetry that we had mentioned earlier, and really this ends up being the first law of thermodynamics, is that energy is conserved. For us, what that means is the heat released from whatever we're looking at if we're placing a hot object in a cold object. So let's just say we have a beaker of room temperature water. We have a hot piece of metal of some sort. We drop it in there, right? Energy is going to transfer from the hotter piece of metal to the cooler water. And so let's say we actually did this in our coffee cup calorimeter, meaning, right, we put it in, we put the lid on, meaning now we know that any of the energy, we're going to assume that this is perfectly insulated so nothing can get in, nothing can get out. Okay. So now we know, if we know how much energy the water gained, right, the heat absorbed has to be equal to the heat that was released by the piece of metal. Okay. And so we can also just say negative Q of the hot, because heat always flows from hot to cold, that the negative Q of the hot equals the positive Q of the cold. Again, this is the negative sign showing that this side is the exothermic side, this side is the endothermic side. All right. So, well, we know Q equals MCAT, so we have the Q, or just the negative MCAT of the hot side, and the MCAT of the cold side. Okay. So the only real tricky part is just making sure you're matching up the right mass, specific heat, and change in temperature. The negative sign here won't be too much of a big deal, right? If we're on the exothermic side, this delta T should come out to be negative, which is going to cancel out with that, and all will be well. There are some more complicated problems where this becomes important if we're trying to find a final temperature, but we probably will not be doing those in this unit. Okay, so let's look at an example. So we take that idea that I was just saying. We've got our coffee cup calorimeter. We've got some water in there. Well, let's say there's 50 grams of water in there. Okay. And we take some unknown piece of metal, and let's say that piece of metal starts off at 100 degrees Celsius, and that piece of metal is 12.1 grams. We put it in there. Our piece of metal is now here. Energy is going to flow from that piece of metal to the surroundings. We forgot to give the water a temperature. Let's say it's around room temperature at 22.1 degrees Celsius. One thing we know for sure is that the final temperature of both of these things has to be equal. So T final equals, or T final of the metal has to be equal to T final of the water. That is another very, very key idea, right? Because energy is going to keep flowing until these two things reach the same temperature. Okay? So we know that the total energy released is going to be equal to the total energy absorbed, and the key idea that the T final of both objects have to be equal. So in our case, we've got negative Q of the metal and positive Q of the water. So what we're really going to find out here is we don't know what this metal is, but what we can find out is its specific heat. This might be another way to identify a metal because each substance has a unique specific heat. So if we can find the specific heat of this piece of metal, we could use that to help identify it. Okay. So there is a way to break this into two steps, right? I know the mass of the water, I know the specific heat of the water, I know the delta T. I actually don't know yet because we didn't tell you. In this scenario, we're just going to say that the final temperature is 23.8 degrees Celsius. Right. And let's look at the logic behind that, right? We have 50 grams of water and about a quarter of that mass for our metal. We know that water has a very high specific heat and metals tend to have a very low specific heat. So we don't expect the water to change very much. We see the water only changed by 1.7 degrees, where the piece of metal changed by almost 77 degrees, 76 degrees. All right, so we know all of that. So we could calculate Q and then plug it in and solve for specific heat like we did on a previous practice problem. I just kind of like to set them all up at one time. Okay. And so we'll just plug in the mass of the piece of metal is 12.1. Remember, this side is the metal. Our specific heat is what we're looking for. Our delta T is T final, which is 23.8 minus 100, which was our T initial. Our mass of our water is 50 grams. Our specific heat of water is 4.184. I'm going to run out of space here. Oops, forgot the units there, but that'll be joules per gram degrees C. And our delta T is going to be our T final, which is 23.8 minus 22.1 or 1.7 overall. All right, so we come back. If we do this math, all right, this works out to 922.02 on this side. Okay. And if we look at what's going to cancel, remember over here, we're going to have grams and degrees Celsius, right? We're going to have joules and grams degrees Celsius over here. So what isn't going to cancel will be what we expect for our units. So I'm going to leave those off right at the moment. We have 355.64. Oops. And this is C times that because that's our specific heat is what we're missing over there. So C equals 355.64. And 922.02. This is joules up here because those canceled to leave just joules. This is grams dot degrees C because grams and degrees C were all that was left. And so we get a value of 0.38386 joules per gram degrees Celsius. So 0.386 is in the neighborhood we expect for metals. Metals are typically like 0.1 to about 0.5. They can go beyond that, but most of the common ones are in that range. And so that's a typical calorimetry problem. It looks a bit complicated, but if we keep the key ideas, that one, the T final has to be the same for both of them, and we have to have most of this information to plug in to solve for something, right? If we knew the specific heat of the metal but didn't know how much the mass was, we could figure that out, or figure out how much water was there. Again, we could figure out a lot of things as long as we have all the information. Okay, so just to give a little summary on that. So remember, we're working with a problem where usually we're adding something into our calorimeter. And so we typically have water in here or something. It could be hot water and we're putting in like a room temperature piece of metal, or vice versa. It doesn't really matter. The key here is, we'll just put a lid on here, that if I have this piece of metal here, if the piece of metal is hot, right, energy is going to be flowing outward, right? But if we had a similar setup and our piece of metal was cold, put a C on there, the energy is going to go from the water to that. Okay. The other key idea here is that this energy is going to continue to flow until the metal, or whatever the object is. I'm just using metal here because that's very common, but whatever we're doing, the metal equals the water. Again, it doesn't have to be water, final temperature. All right, so they're going to keep going until they reach the final temperature. And this could actually even be hot water mixing with cold water. So when you do that at home, if you have a hot water faucet and a cold water faucet, you turn them on so that they mix together to come to a certain temperature. Right? It simplifies a problem a little bit because we know water has the same specific heat, and so mathematically it makes it a little bit easier. But you would still do the same problem. Remember, whatever energy the hot thing loses, the cold thing has to gain. And again, we're ignoring any energy that the calorimeter might absorb and assuming none is lost or transferred to or from the calorimeter, right? So we don't get any of that. So that's our foundation of calorimetry. The rest is just keeping track of what goes into the equation and using your calculator effectively.
Have you seen Junior's grades?